We wanted to figure out what a to the seventh was, given the information that, that we have eigenvectors 1, 1, 0, 0, 3, 2, 1, 2, 1, and we have corresponding eigenvalues -1, 0, 1, right? So to get a to the seventh, this would be p, the inverse to the seventh. And I think most people notice this, p, d, the inverse, plus p, d, the inverse, plus p, d, the inverse. What would happen is that these p inverses and p's would pair up so that you just get I. So all of that goes away. P, yeah, exactly, d to the seventh, p inverse. And now, it was a matter of noticing what d to the seventh was. And because it's an odd power, d to the seventh is exactly the same as d. So this is just p, d, the inverse. And at this point, most people did a multiplication, but this is just a. So you had to do absolutely no computational work in this problem at all. Most people, I think only one person actually noticed that.
I was thinking, I was like, man, I don't have much room to write this out.
Yeah, that was a subconscious hint. So yeah, that's another matrix factorization, and there's lots of them. But today we will talk about what's possibly, it's definitely up there in the most important, LU factorization, the similarity transformation, the factorization that gives you. What is that called? It's called something decomposition. I can't remember the name. Anyway, decomposing it as its eigenvectors and eigenvalues. Very, very important. Factorization or decomposition. And the one we will talk about today, which is based on orthogonal matrices, is at least as important. It is called QR. Factorization. As I was writing, I realized that this part of the Graham-Schmidt process is exactly what I wanted to have on the, yeah. Some chat, please. U2 equals V2 minus V2W1 over U1W1 U1. Which I'm just going to write as, let's leave it like that. Yeah, okay. And then U3, I want another example. V3W2 over V3W2 in the V3 direction. And this continues on for the rest of them. Okay. So, what do we notice about this? We notice that not only are we taking the original vectors and using them to get orthogonal vectors, we could really go in the opposite direction. This tells us, well, how do we get V1? It's just U1. How do we get V2? It's U2. Plus, I'm going to write this as R2, I'm going to use the same convention as the book. U3. I just add these over the other side, and I've got U3 plus something times U1 plus something, I'll call it R23 times U2. V4 is equal to U4 plus R1 or U1 plus R2 for U2 plus R3 for U3 and so on. Now there's nothing surprising about the fact that we can rewrite our original vectors as linear combinations, right? This is a linear combination of U1, this is a linear combination of U1 and U2, this is a linear combination of U1, U2, and U3, this is a linear combination of U1, U2, U3, U4, and so on. There's nothing surprising about that because we know that these are bases for the same space. We should be able to take anything in the original basis, or we should be able to take anything, any of the u's and rewrite them in terms of the v's, and we should be able to take any of the v's and rewrite them in terms of the u's, right? Because they span the same space. So they're bases for the same space. What is interesting is that we know exactly what the linear combination is. We know it, and there's a 1 in front of all of these. Right? We know exactly what the linear combinations are. So if we want to get, let's say, let's write it like this. Okay. So that's our original vectors. If we want to construct these as linear combinations of our orthogonal vectors, how do we do it? Well, so it's going to be every column of this is multiplied as across this row, right? So this will give us a linear combination of these vectors. The first one is 1 and a bunch of zeros. Right? The next one is R12, 1, and a bunch of zeros. Because I'm going to take this much of U1 and just 1 of U2. What about the next entry? V3. It's inside the ellipsis. It's going to be R13, R23, 1, and a bunch of zeros. And we see how this continues. So what we got here, the dot, dot, dot means you get it. At this point you get it, right? We have all of these relationships. We have these linear dependence relationships. Previously we had been trying to write linear dependence relationships with the zero vector, but there's still dependences. And, well, if we subtracted this over the other side, it would be something equal to 0. So we're taking these linear relationships and we're using them to construct this matrix right here. And what's special about the structure of this matrix? Yeah, it's upper triangular. And which we will call, U is already taken, so we'll call this R. And orthogonal, for some reason, call that Q. And this is our original matrix A. So we get A equals QR, and this is the famous QR factorization.
So this is just another way of representing basically what we already know from the branch.
Yes, it is. However, I'm trying to think of how, there's no way I'm going to be able to explain this. This is the Well, first thing, this is, like I said, this is just the theoretical basis for it. In practice, that we use another method. So we apply a series of orthogonal, a series of multiplications by orthogonal matrices to A until it becomes an upper triangular matrix. And then we take that as, because all of these are orthogonal, transfer. The product of orthogonal matrices is again an orthogonal matrix. I'm trying to think if that's an easy thing to justify. I don't think the book justifies it, so I'm not going to try to. But this factorization is the basis of the method that's used in practice to compute eigenvalues and eigenvectors. So the QR method is what's used in practice to compute those things. And I don't think the book goes into that. And if I recall correctly, from a long time ago when I learned the method myself, it was a little bit of work in order to show how it works. But anyway, this is another factorization that we have. And it's, in practice, a very important factorization. So,
It kind of makes sense. I mean, if you multiply two orthogonal vectors together, you get one orthogonal to both of them, right?
That's the cross.
You get
That's-
a normal vector.
so
So if you do it with
that's-
a matrix, it kind of,
that's a different kind of multiplication.
never mind.
So it's, I'm actually glad you brought that up because on the exam, there was this question, and you asked about this as well. Let's look at it. Because we got about 4 minutes left, there's not enough time to jump into something new. So it's a different kind of multiplication. When we do the dot product, we don't end up with another factor. Just like when we had the dot product in Calc 3, we called it the dot product then, or the scalar product.
That would be our product, okay.
Yeah. So we had the dot product and the cross product, or the scalar product and the vector product. Now the cross product, there's something interesting about this. Whenever we were talking about, for example, R2 and the complex numbers. These are isomorphic as vector spaces. But in the complex numbers, we have a multiplication. And in R2, we don't. We have the dot product, which gives us a scalar. When we multiply two vectors together, we get a scalar. We don't get something else inside here. But in the complex numbers, we can multiply two complex numbers together and we get another complex number. And what I tried to show was that that multiplication is not represented by the dot product. It's not represented by something like the cross product. It is instead represented by a matrix multiplication. So we can take an element of C and we can find a matrix, a 2 by 2 matrix, that represents that element, both with addition. So we add two of these together, it represents the addition in C, and also the multiplication in C. It represents the complex multiplication. But we don't have anything like that in the vector structure of R2. So similarly, in R3, we have addition, we have scalar multiplication, it's a vector space. But we also have cross product, right? We also have this extra piece of arithmetic. And this cross product, when we do it in R3, it actually does not exist in R2. There's not a corresponding concept in R2, and there's not a corresponding concept in R4. There's a corresponding concept in R7, though. There's a similar thing to the cross product. but it depends on it being, well, I'm not gonna go into it. I'll just say there's a cross product. However, it has a lot of bizarre properties. For one, you remember, you take the cross product of two things that are perpendicular to each other and you get 0. Or, no. Take a cross product of something with itself. There we go. I cross K is equal to K. So the cross product of something with itself is 0. And that's a weird property of multiplication that we kind of, well, it has a lot of strange consequences. It's inconvenient. Nothing like that happens in C. Nothing like that happens in R. There's no two things that you can multiply together to get 0 unless one of them is 0, right? So we can no longer say A times B equals 0. That means A or B plus B equals 0. Not with this multiplication. It's also not commutative. Well, matrix multiplication wasn't commutative. But let's say U cross V is equal to, it's not equal to V cross U, but if you switch the order, it becomes negative as well. So that's another strange property of this multiplication. Now, that's to take the thing that you're talking about and put it into context. There is this multiplication, and it has a lot of the properties that we would want of a multiplication, but it's got some kind of weird properties as well. However, it does have one very interesting property, where if you say U cross V equals W, then W is orthogonal to U, and W is orthogonal to V, or we could say W dot U is equal to 0, or W dot V is equal to 0. Now, the point of all of this, if we have two vectors, 1, 3, minus 3, 0, 2, 2, we want to find a vector V that's orthogonal. Let's say that W is the span of these. V belongs to the orthogonal complement. There are a lot of different ways that you could do this. You could just come up with a vector and just say, this is a random vector. I'm going to do the orthogonal projection into W. See if there's anything, and so there's a part in W, see if there's an orthogonal part. If there is, I've definitely found something that's orthogonal to W, the orthogonal part. That's kind of what the Gram-Schmidt process does. But because this is R3, because these are three-dimensional vectors, we have the cross product. So you could have just taken the cross product of these two things. You got an orthogonal vector. I don't know if anybody did that or not.
I have a question. I was thinking about this the other day, because I was thinking about this question on the exam. Is there well, I can't think of a way off the top of my head that if you pick like the identity matrix for that, so 0, 0, 1 in the last one, I can't think of a way that wouldn't be orthogonal to everything else, right? Because like if you row reduce it, you'll get the identity matrix, and then that means they're all, well, they're not orthogonal, they'll all be linearly independent. So does that mean like for R and the identity matrix for like n plus 1 is always orthogonal? Or the identity elementary vector? I'm sorry, I missed that. No.
So if these were our two vectors,
So when it,
or what you were talking about, I think was this one. So if these were our two vectors, then this is certainly not linearly independent from itself. So that's a situation in which it would not be true.
Okay.
We always have to check. Now there was something in the book, this is another hint, for doing things in a purely linear algebra way. Of course it's after 150, so you don't have to stay. Some people are looking just a little anxious. And where was this? So this was in 6.2 maybe?
Is it the column space and null space?
That's right, you got it.
That's what I did.
So, well, we don't even have to look at it. Let's do it directly on this problem. So it was 1, 3 minus 3. transpose, you look at the null space. Okay, what is, taking the transpose and doing the null space, I could follow these directions, certainly. I know how to take the transpose, I know how to find the null space. But why? Why is that what I'm doing? Let me call this one V1, and this one's V2. I believe I saw you do that on your. Okay. So what are we looking for? We're looking for something, say V3, that V1 is equal to 0, V2 that V1 is equal to 0. So I want to find V3. So V3, I'm just going to call it A, B, C. I take the dot product with this, I get A plus 3B minus 3C equals 0. That's what I want. And for this one, I want 0 plus 2B plus 2C equals 0. Right? And then I solve this system of equations. This is just another linear system of equations, just like all the other ones that we've done. And we can write this one as a matrix vector multiplication. And that, of course, is 1, 3, minus 3, 0, 2, 2.
And then all the non-trivial solutions, right?
Which is precisely finding the null space of the transpose of the matrix.
Does that still work if like, if we were given like a set of 3, so if it was like it would make like an invertible matrix, right? So then that would be messed up. So if we had 3 vectors of dimension 3, then if we were doing that trick, that'd make an invertible matrix. I feel like that would complicate
It would complicate it to the point of not being able to do anything,
it.
right? Well, because we have 3 vectors and we want something that's orthogonal to all 3, if it's orthogonal, it's got to be linearly independent. But that's the whole space. 3 of them is the whole space because it's dimension 3.
Okay.
So there's nothing else to add in.
Okay.
So you just wrote the R2 vector there. Did the orthogonal vector was in R, would end up being in R3?
Oh, right here.
Yeah.
This is what I'm trying to solve for, A, B, C.
Right. Okay.
So this would be something in the null space.
So it was sufficient, or I think it was sufficient to go ahead and find an R3 vector that was dot product was 0, right? And that would be for part A.
Is the dot product with each of them?
Yes.
So the dot product with this and the dot product with this.
And then for part
Simultaneously has to
B,
be.
I just dot product with the new vector and said basically it's not orthogonal to this vector, so it can't be W.
If it's, everything in W will be orthogonal to the new vector.
Okay, that's what I wrote, then I erased it.
Oh, well, I didn't see that,
I
but
wrote over.
I started to write that if it were R4, then just because it was orthogonal or something, well, no, because it wasn't orthogonal. But in R4, if it was orthogonal to your new vector, it wouldn't necessarily prove that it's or that it's in W, right?
it would.
Because
It would. Because we have W, this is W, right? And this is our new vector, perpendicular to it. Everything in W is perpendicular to that new vector. So anything that's perpendicular has to be, and it switches the other way. This is perpendicular to this. Everything that's perpendicular to this is all of this. Yes.
So that's why I erased it, because I guess when I was like writing, I got really confused, but because I was thinking of that example where we're projecting on the line and Y isn't in the space of W, but it's not necessarily orthogonal to it. So if it's orthogonal, it's excluded from the space, but if it isn't orthogonal, it's not necessarily included.
Right.
So if the angle is
let's think in the three-dimensional case. So this is a decomposing, it's not the whole space, right? We have the space, let's call this our W, and this is our W complement, orthogonal complement. They don't add together to give you the whole space, right? There's stuff that's not in this plane, but it's not orthogonal to it either. So yeah, that's true. Like if we had something that's outside of W, we took the dot product with something that's in W and it didn't give us 0, that doesn't tell us that whether or not it's in W. Now if it gave us a dot product of 0 with something in W, that tells us that, doesn't tell us that it's not in W either. However, if we have a vector that's perpendicular to all of W, and this is in 3 dimensions, but in 4 dimensions we would have a 3-dimensional space, and then we have a 1-dimensional orthogonal complement. It's hard to imagine what that would look like, but there's a 3-dimensional space, subspace in the 4-dimensional space. And then there's an orthogonal complement to that that's just a 1-dimensional, it's a line in 4-dimensional space, straight line. It goes to the origin, goes to the 0 point. If you want to know if something's in that 3-dimensional space, you only need to check if it's orthogonal to the thing that's orthogonal to everything in that space.
Yeah, I got mixed up in my head.
So we're talking about a 4-dimensional space, but W is still a plane, 2-dimensional, and
That's why I try to be careful when I talk about this example. This is an example in 3 dimensions, right? So it's the floor is W, and then W orthogonal to W is wherever we pick the center of the floor to be, right here. It's a line coming straight up.
Yeah.
In 4 dimensions, we could have a 2-dimensional subspace, and then look at the orthogonal complement. And the orthogonal complement would itself be a 2-dimensional subspace.
Okay, so you can't have an orthogonal, you can have the vector orthogonal to it, but it won't be an orthogonal complement.
No, it won't be the whole complement.
I
That's
see.
right. So just one vector is enough. It gives you one of the orthogonal directions, but in
Yes.
4 dimensions you would have 2 orthogonal
Okay,
directions.
so you have to have a full orthogonal complement to prove that, because if you only had one vector orthogonal to it in 4-dimensional space, then the dot product wouldn't prove that it was in W, because it
It
could.
would. It would. Because if we think about this, let's say, I don't know how to draw this, but, okay, this is our orthogonal complement, right? We only need one thing, and everything in here is orthogonal to everything in here.
But you have to have a 2-vector basis for that, right?
No, any one vector in here, anything, any one thing, just, you only need one. That one thing will be orthogonal to everything down here.
Okay.
So, like I said, this is a 2-dimensional space. You can find 2 orthogonal vectors, which are orthogonal to this. If you want to find out if something is in here using that orthogonality, you only need to check one of them, because everything in here is orthogonal to everything in here and vice versa.
Yeah.
Just like expanding on that, you're saying if it's orthogonal to the space, and you have the thing that's orthogonal to that, so that's why it just more concisely checks that instead of checking if it's orthogonal to each basis. You can just kind of take a shortcut and see if it's orthogonal to the thing that's orthogonal to both of them.
The important fact is that if you have a space and you have its orthogonal complement, everything here is orthogonal to everything here, and everything here is orthogonal to everything here. So if I want to find something in here, all I have to do is check if it's orthogonal to one thing over here, right? That's the, I'm kind of losing the thread now. In a 4-dimensional space, if we had a 2-dimensional subspace, its orthogonal complement would also be 2-dimensional. We could find 2 other directions besides also have a three-dimensional subspace, in which case we would only have a one-dimensional orthogonal column. At this point, I don't know if I'm answering any questions, or not. I'm just talking. Everybody's so nice, they just stay here.
It's got me thinking about string theory. Ever since you said that 7-dimensional thing, like we have a, equivalent in 7 dimensions.
Well, I probably shouldn't start on a new topic, but what it has to do with is, so in R3, the reason that we have a cross product is because there's an associated product that's like the complex multiplication in the space of quaternions. And so this cross product it corresponds to that in a certain way. So when you go to the next example of something that has a multiplication that's similar to this complex multiplication that's in the octonians, and one dimension lower is R7. So that's the reason why that happens.
Do we learn about the cross product in this class, or?
No.
Like specific? No.
Because it doesn't relate to, it doesn't relate to vector spaces. It's specific to a vector space, specifically R3. R3 is the only place that happens. If you want to think about weird connections with the physical world, we live in three-dimensional space, and there's a cross product in 3 dimensions only. So there you go.
This is really random, but like, I always hear that in like physics class, we live in a three-dimensional world, but how would we know that we don't live in, with more dimensions that we just can't see? Like, because we view the world in 2 dimensions, we exist in 3 dimensions. How would we, what would we even see if there was a 4th dimension? Like, how do we know that that doesn't exist just because we can't see it?
Well, that's the thing behind string theory. It's actually posited that there are 10 dimensions, with the 11th being time, because the math works out that way. And that basically all the other dimensions are so small, curled up, flat, that we can't perceive them because they're so small. Imagine you were a cartoon character, and actually you had a very